and welcome to today's physics lecture, wherein we shall be taking a deep look about the electromagnetic induction. Right? In the year 1820, it was proposed by Oersted that due to the change of electric field, or for example there is a circuit over there, electric current is passing, so it can generate the magnetic field in its vicinity. After that, in the year 1831, the converse to this has been experimentally detected by the famous physicist Faraday. Now what Faraday actually observed in the famous Faraday's experiment is that if the magnetic flux is being changed with respect to time, an electric current is being produced. Now the phenomenon by which an electric current which could be produced due to the change of magnetic flux in a circuit is known as electromagnetic induction. Now, the point may be noted about magnetic flux. We have learnt about the magnetic field, the magnetic lines of force. Now, what is this magnetic flux all about? For example, we take a particular area. Say for example this is an area, and all of us we know that the vectorial representation of the area, it is always normal or perpendicular to the plane of this area. So if this area is being tilted, right, for example take my hand, it has got this area. Now I have kept it likewise, so the area will be on this side, right, and the vectorial representation of the area will be like this from my hand on this direction. It will be perpendicular to the plane, right? So this is A. Now for example, a magnetic line of force or magnetic field is enacting in such a way that it makes an angle of say theta with the vectorial component of A. So here comes the concept of magnetic flux, that the magnetic flux which is denoted by phi, so the magnetic flux will be equal to the dot product of these two vectors, right? And from the vectorial notations we know that a dot product of two vectors will always give a scalar product, I mean a scalar quantity. So this thing, or phi, your magnetic flux, will be a scalar quantity, and the formula will be the magnitude of this B, or magnetic field, multiplied by the magnitude of the area, that how much area is it, and multiplied by cos of the theta, right? So this is the expression for the magnetic flux, where phi is equal to the magnetic flux, right? So if phi is equal to the magnetic flux, so we can see that this phi is equals to BA cos theta, right? Now from the Faraday's experiment we know that if suppose for example this is a coil if we bring a bar magnet such that, for example, say this is the North Pole and this is the South Pole, nothing will happen. But on the contrary, if we start moving this bar magnet either towards this coil, or if we move this bar magnet away from this coil, a change of magnetic flux is happening with respect to time. And the electromagnetic induction, it says that the time rate change of magnetic flux will produce an electric current or an electric field, or it will induce an EMF, or it will induce some charge. We will be going into everything, but first of all, we would like to know the SI units. The SI unit for this B is Tesla, or this is denoted by T. And the SI unit of this magnetic flux will be Tesla meter square, because area always in meter square in SI units. So this phi will be Tesla meter square and is also known as Weber. Right? So this Tesla could also be said as like Weber per meter square, or Weber could be said as Tesla meter square. Now let us come after this Faraday's experiment about the Faraday's law, the law which were proposed by Michael Faraday. The first law states that whenever there will be a change in the magnetic flux and induced EMF, and consequently an induced current will be generated in this circuit, right? But that induced EMF or the induced current will be over there only up to the limit or the time up till this magnetic flux is changing. If the magnetic flux changing ceases or it stops, the induced current or the induced EMF will stop then and there. Right? So it says that whenever a change in magnetic flux or phi happens, an induced EMF and consequently an induced current gets into action, but this will be until that time up till which this change of magnetic flux is happening. Okay? But from this Faraday's first law, you may ask that for how much change of this phi or magnetic flux, how much induced EMF will occur or how much induced current shall occur. Because this does not say us anything about the magnitude of induced EMF or the magnitude of this induced current. Now that could be answered by the Faraday's second law. Now in the Faraday's second law, it is proposed that you can see from the Faraday's first law that whenever there is a change in phi, an induced EMF or an induced current take place. But for how much change of this phi, how much EMF shall be induced? Or for how much change of phi, how much electric current shall be induced within a circuit? That is being given by Faraday's second law. In the Faraday's second law, it says that the induced EMF in a circuit is directly proportional to the rate change of magnetic flux. Right? So, if we take that E equals to induced EMF, so as per the Faraday's second law, it states that E will be directly proportional, right? Directly proportional to d by dt component of phi. But if we want to change this proportionality constant into the equality constant, we could take as such that E will be equals to K of d phi by dt, right? Now, this is in accordance with the Faraday's second law. But if you do observe very closely about the Faraday's second law, you will find that the Faraday's both the laws does not give us anything, or it does not tell us anything about the direction of this induced EMF. Right? This could be answered by the famous Lenz law. The Lenz law says that the EMF that would be produced or induced within this circuit in such a way that it opposes the change that is producing it. Now, which change is producing it? Obviously, this phi. This phi change with respect to time is going to produce this induced EMF, right? And this induced EMF will be as such that the direction will be as such that it will oppose the change that is producing it. So now this equation will be equals to minus of k d phi by dt, right? And if we take the units in such a way that k becomes equal to 1, we can write the equation as E will be equals to minus d phi by dt. So this is the expression for this induced EMF, which is in accordance with the Faraday's laws and as well as the Lenz law. Now in the Lenz law, it has been said that this mechanical energy, right? This mechanical energy is happening because we have to move this bar magnet so as to produce a change in this magnetic flux, and then the current will be induced within this circuit. So the mechanical energy is now getting converted into the electrical energy. So this Lenz law is in accordance with the law of conservation of energy, right? Now, if we could recapitulate about the famous Ohm's law, which states that V equals to IR, where the V is the potential difference between the 2 points. For example, these are the 2 points. This is the potential difference V will be equal to the induced current multiplied by the resistance of this entire circuit. So where R will be equals to resistance of the circuit, right? And I will be equals to the induced current. Right. So you can see that this V, or the potential difference, is an analogy with this E or this induced EMF. So we can put IR instead of E, right? So now let's see what happens. If we keep this IR is equals to minus d phi by dt, then the I, what is I? The I is the induced current. This I will be equals to minus of d phi by r dt. So this was the expression for induced EMF, and now this is the expression for the induced current. Now we know another formula as this I could be stated as dq by dt, where the Q is equals to the induced charge. The charge which has been induced in this circuit is dq. So in this place of this I, if we put dq by dt, now let's see what happens. dq by dt will be equals to minus of d phi divided by r dt. So this q will come up to be minus of 1 by r, the integration of d phi, because dq was the small induced charge for the small change in magnetic flux, right? So for getting the entire induced charge within the circuit, we have to integrate this phi, or the magnetic flux. So the expression will come as Q will be equals to change of this phi, or the magnetic flux, divided by the resistance of the circuit. There is no negative sign in this expression because we are actually interested to understand that how much charge actually gets induced in this circuit for the given change of magnetic flux, given that this circuit has got a resistance of R. Right? Thank you.